Synchronous motor drives. Synchronous motors have polyphase winding on the stator, also known as armature, and field winding carrying a DC current on the rotor. There are two MMFs involved. One is due to field current and another is due to armature current. The resultant MMF produces the torque. The armature is identical to the stator of an induction motor, but there is no induction in the rotor. A synchronous motor is a constant speed machine and always rotates with a zero slip at the synchronous speed, which depends on the frequency and number of poles. A synchronous motor can be operated as a motor or generator. The power factor can be controlled by varying the field current. The cycloconverters and inverters are widening the applications of synchronous motors in variable speed drives. The synchronous motors can be classified into 6 types. First one, cylindrical rotor motor. Second one, silent pole motors. Third one, reluctance motor. Fourth one, permanent magnet motor. Fifth one, switched reluctance motor. And finally, sixth one, brushless DC and AC motors. We will study about these 6 types of synchronous motors in detail in coming videos. The first type of synchronous motors are cylindrical rotor motor. The field winding is wound on the rotor, which is cylindrical, and these motors have uniform air gap. The reluctance are independent on the rotor position. The equivalent circuit per phase as shown here, neglecting the no load losses, where RA is the armature resistance per phase, XS is the synchronous reactance per phase, VF, which is dependent on the field current, is known as excitation or field voltage. The power factor depends on the field current. The typical V curves, which are shown here, shows the variation of armature current against the excitation current, IF. For the same armature current, the power factor could be lagging or leading depending upon the excitation current. If theta m is the lagging power factor angle of the motor, then Vf is given by Va at an angle 0 minus Ia of Ra plus J XS. Question number 1. Then this we can write as Va at an angle 0 minus Ia of cos theta m minus J sin theta m of Ra plus J XS. That equals to Va at an angle 0 minus Ia XS sin theta m minus Ia Ra cos theta m minus J Ia of XS cos theta m minus Ra sin theta m, which is nothing but Vf at an angle of delta, where delta is equals to tan inverse of minus Ia XS cos theta m minus Ia Ra sin theta m divided by Va minus Ia XS sin theta m minus Ia Ra cos theta m. That is the equation number 2. The magnitude Vf is given by Va minus Ia XS sin theta m minus Ia Ra cos theta m whole square plus Ia XS cos theta m minus Ia Ra sin theta m whole square, the entire thing under the square root. Let it be question number 3. From the phasor diagram, Vf is equals to Vf cos delta plus J sin delta. Let it be question number 4. Ia equals to Va minus Vf divided by Ra plus J XS, which equals to Va minus Vf cos delta plus J sin delta of Ra minus J XS divided by Ra square plus XS square. Let this be equation number 5. Now, from equation number 5, the real parts will become Ia cos theta m equals to Ra Va minus Vf cos delta minus Vf XS sin delta divided by Ra square plus XS square. Let it be equation number 6. Now the input power Pi equals to 3 VA IA cos theta m. Now substituting IA value from this equation, we are going to get 3 RA VA square minus VA VF cos delta minus VA VF XS sin delta divided by RA square plus XS square. This is equation number 7. Now the stator, which is nothing but armature copper loss, is given by PSU equals to 3 IA square RA, let it be 8, and the gap power, which is same as the developed power, that is PD, which equals to PG, which equals to PI minus PSU. Let it be equation number 9. If omega s is the synchronous speed, which is the same as the rotor speed, the developed torque will become TD equals to PD by omega s. Let it be equation number 10. If the armature resistance is negligible, then TD will become minus 3 VA VF sin delta divided by XS omega s. Let it be equation number 11. From equation number 2, the delta will become minus tan inverse of IA XS cos theta m divided by VA minus IA XA sin theta m. That is equation number 12. For motoring, delta is negative and torque become positive. In the case of generating, delta is positive and the power will become negative, or the torque will become negative. The angle delta is called torque angle. For a fixed voltage and frequency, the torque depends on the angle delta and is proportional to the excitation voltage Vf. For fixed value of Vf and delta, the torque depends on voltage to frequency ratio, and constant volts per H control will provide speed control at a constant torque. If VA, Vf and delta remains fixed, the torque decreases with the speed and the motor operates in the field weakening mode. If delta is 90 degrees, the torque becomes maximum, and the maximum developed torque, which is called pull-out torque, is given by Tp equals to Tm equals to minus 3 VA Vf by XS omega s. Let this be equation number 13. The plot of developed torque against the torque angle delta is shown here. For stability consideration, the motor is operated in positive slope of TD delta characteristics, and the limits, the range for the torque is minus 90 degrees less than or equal to delta less than or equal to 90 degrees. This is regarding the cylindrical rotor motor. If this video is useful, please like, share and subscribe.